Hello, I'm Dr. Satish Rao, Professor of Medicine. Today we will talk about a new neurophysiological test, TAMS, that stands for Translumbosacral Anorectal Magnetic Stimulation Test. We will talk about its measurement and interpretation using the Nihon-Kohden system. We completed a recording on a patient with bowel problem who we've identified as TAMS 01 with initials JC that you will see on the computer behind me. Here is the patient's recording, and what you will see, we will double click on this. It opens up a menu with the label as TAMS, lumbar and sacral, and we stimulate the patient at 4 recording sites: left lumbar region, left sacral region, right lumbar region, and right sacral region. And we have 4 file folders, each containing the recordings on this patient. We will open up the file folder labeled left lumbar, and then immediately you will see a set of multiple waveforms which represents the entire recording on this patient. As you can see, everything looks a little gibberish to begin with, and what you do is first go down to this box called Position Superimpose. You click on this and initially it completely groups all of these traces. You then click again saying Separation by Channels, and now you see them grouped under the rectal waveforms, which is the top, the anal waveforms, which is the middle, and the leg waveforms, which is the lower part of this. You then go up to the top corner, and then you can highlight any of the channels that you wish. Here you can highlight a single individual wave, here you can highlight a group of waves, and this is all waves. So first we will come down and we will move the leg tracings out of the way so that we open up the screen to more carefully explore and measure the rectal waves. I'm moving the anal waves down and give more room for us to study the rectal waveforms, which is now in the center of display. Now we have grouped all of these waves. Just to give you an orientation, the horizontal scale is the time scale, and this is in 3 milliseconds. In other words, a deflection from this point to this point is 3 milliseconds. And the vertical wave is the amplitude, which currently is set at 100 microvolts. But here you can see the individual waveforms of different microvolts, and when we open it up, you will understand this better. So we have all the rectal waves grouped together. We will now slowly go up to this channel, hit this single individual channel because we want to measure individual waves, and I'm going to try and separate them so that you can now see a very nice waveform. The computer has been programmed to measure the waveforms as positive and negative deflections, and it has already done that. And so we're going to try and look and see whether these waveforms are reproducible. As you can see, as I'm moving up, I have at least 3 waveforms that are very, very identical. So we can pick on any one of these, and today for learning purposes, let's pick on H1, for example. Let's see, here is the H1 wave, and that's a nice wave. I'm going to move this down a little bit so that we can focus on the H1 wave. So on the H wave, the computer has already calculated the P1 latency, the N1 and P2. If it is not properly marked, you can always use this and move it around until you get the right waveform. So if you agree with this measurements, you then go to the right hand corner. You know this is wave H1. You want to identify that wave by scrolling down, and there is H1, and you can see for P1 the latency is 4.4 milliseconds, which is what you will make a notation of. You then want to measure the amplitude of this wave from P1 to N1. And this is already set as H1 because you've highlighted H1, and it gives you an amplitude for P1 to N1 as 114.4 microvolts, which is good because you want this to be at least 10 microvolts or greater to call this a true wave and not an artifact. The next measurement is the area under the curve, for which you need the P1, N1, P2. That is the area you're measuring as an overall measure of the robustness of this wave, if you like. And the H1 is the area already set, and the value is 184.3 microvolts times milliseconds. This is how you will measure the left lumborectal motor evoked potentials. Having completed that, we can then group all of this rectal waves together and then gently push them out of the way, if you like, and then now group the anal, bring it up, and then we're going to focus on measuring the anal waves. Again, I'm going to separate out some waves because I think some of these waves quality are not the best. So let's pick a wave. Let's say, how about we look at A1 here. So one of these waves will turn out to be A1. So let's see where A1 is hiding. It may be up here. That's K2, D2. D2 is fine too. We can also use D2. How about we use D2 here? Here is E2. They're all good waves. We can see a nice clear takeoff, and that's another nice wave as well. So B2 is nice. So you can see the computer has already marked this. I usually like to move this a little bit because I like to see the takeoff point. So that is P1. N1 is good, and P2 is when the waveforms have completely ended. I've just gently moved this a little bit. Now we go back to B2 here and go up a bit. There is B2. P1 is 3.9 milliseconds, which is the latency, which is again good and normal. We come down. Now here it says D2. I'm going to change that to B2 for both the amplitude and the area. And you can see the amplitude of this waveform is 192 microvolts, and the area is quite big, which is 1317 microvolts per millisecond. So that's a very nice, good quality wave recording in this patient. Now let's go to another site. Let's take the sacral left side. Again, you see the whole waveforms. We will repeat the same kind of maneuver. We will do the position superimpose first. We will click that first. We'll click it again. All the waveforms are separated. We will then go to the individual channel waves. I'm going to highlight the leg once, move it down. I'm going to highlight the anal once, move it further down. I'm going to highlight the rectal ones. Then we go up again and go for the individual channels of these waves. And then now let's try and separate. Now that's a very good wave. But the interesting thing here is, I'm not going to open up the other waves, but just let's focus on this. The computer has marked the positive deflection. But what you see here though is the most prominent first deflection is indeed a negative deflection. So I'm going to move the P1 here, move the N1 down here, and move the P2 up here, because this is the first nice waveform which represents the MEP response in the rectal area. Again, the waveform we've chosen is E1. We will go back to E1 here. You see the latency for P1 is 2.3 milliseconds. The amplitude is 25.9 microvolts, which is smaller than the one we measured before, and the area is 46.8 microvolts. Very good data. Now let's move on, and then we will go and measure the anal. Again, I'm going to try and separate the waveforms here. How about we look at B2? I think I like B2 is good. Another one could be, let's see, E2 is also fairly good. But let's look at B2. I like B2 because I can see a very nice takeoff point here. And I think the computer is fairly accurate. That is the P1, that is the N1, I'm going to bring down P2 to where the curve actually ended. So now we go back and look at B2. Here you see the P1 is 4.9 milliseconds. That's almost at the upper limit of normal to abnormal. The amplitude is 69.8 microvolts and the area is 359 microvolts. If you decide to go and measure G2, for example, you highlight G2, you again check that the takeoff is good, you move this one around here, and then you will have to change the amplitude from B to G, area from B to G, and now you have the data for G, which has a bigger amplitude and a bigger area under the curve. So this is how you will measure all of these various MEP complexes. It's a relatively easy, simple measure, but hopefully I think I've given you some quick perspectives on how to measure the latency, the amplitude, and the area under the curve, and this is how you will typically measure and interpret the TAMS test. Thank you.